Hi guys, so we are going to fly today through some of chapter 8. I want to get through all of the, I want to do the dipole moment because we didn't do that, and I want to make sure we cover dipole moment. I also want to go through all of the Lewis structure stuff, which is including resonance and also including maybe expanded octets or exceptions to the octet rule. So I want to do all of those. So let's look here for our... Let's start, I think we're starting slide number 19, nope, I lied, slide number 20, which is the polar covalent bonds. We're going to start with that dipole moment again. In terms of, and I just want to review it because I think that maybe I think in 4th bell we started it, I don't know that in 7th bell we did, so let's just go over it. We think about polar covalent bonds, and we know that that happens because we have two atoms are sharing electrons unequally. So we have this unequal sharing of electrons, and we can signify this unequal sharing by using those partial charges. Remember, we could have a partial positive, we could have a partial negative charge. So just in case we don't remember that, it's the delta, so delta negative, or we'll do the delta positive. So that lowercase Greek symbol delta is just going to indicate that we have a partial charge that's present. Now, because we have these partial charges, we know that that's a dipole. So the addition of these partial charges, or the showing of these partial charges, means that we have a bond dipole. Now, nonpolar compounds, we know, share equally, and they do not have dipoles. So my polar covalent are the ones that are going to have the dipoles. We can quantify an actual dipole, or we can quantify polarity. And we do that by using something called the dipole moment. So we can actually calculate really how much polarity there is in an interaction between two charges here. So when we have two electrical charges, they could be of equal magnitude but maybe opposite in sign, and they're separated by some distance. That's where we're going to have some dipole that's established. So our dipole moment has a particular formula that's associated with it, and that is our mu equals QR. So mu is going to be representing our dipole moment. Q is going to be representing our charge, and R is just going to be representing the distance that's between those two particular particles, or between those two charges. So remember, Q is charge. We measure charge in coulombs. R is some distance, so we're going to measure that in meters. And mu, dipole moment, could be, we can think about it in coulomb meters, but more typically we measure it in debye, which is symbolized with a big capital D. And on our conversion factor here, we need to make sure that we remember our conversion factor, and that is that in 1 debye, there's 3.34 times 10 to the negative 30th coulomb meters. So 1D here is equal to 3.34 times 10 to the negative 30th coulomb meters. So please make sure that you have that this number equals 1 debye, 1D. Because if we do this formula, we're going to get coulomb meters. But we want to